Now we determine the potential energy stored in a system of two-point charges. Let us consider two-point charges Q1 and Q2 separated by the distance r sub 1, 2, where the two-point charges can be like or opposite charges. In order to increase the distance between them, we need to do some work against the electric field due to the system while displacing any or both of the point charges. The work done in this process is positive for opposite charges and negative for like charges. We can interpret this work as the potential energy stored in the system of the point charges Q1 and Q2, which can be converted into other forms of energy. If we allow opposite charges to move freely, then they start to accelerate towards each other, and their potential energy is converted into the kinetic energy of their accelerating mass. The potential energy of the point charges Q1 and Q2 can be measured by determining the work done while one of the point charge is brought from infinity to a point where the distance between the 2 point charges becomes r sub 1, 2. For example, we can bring the point charge Q2 from infinity to the point P2 at the distance r sub 1, 2 from the point charge Q1 at the point P1. Then the work W is equal to the product of the charge Q2, and the electric potential phi1 due to the point charge Q1 at the point P2 given by the position vector r2. Here the potential due to the point charge Q1 measured at the distance r sub 1, 2 from the point charge is given by 1 over 4 pi times epsilon naught, times the ratio of the charge Q1 to the distance r sub 1, 2. We obtain the same result if we compute the work done while the point charge Q1 is brought from infinity to the point P1 at the distance r sub 1, 2 from the point charge Q2 at the point P2. In this case the work W is given by the product of the charge Q1, and the potential phi2 due to the point charge Q2 at the point P1 given by the position vector r1. Here the potential due to the point charge Q2 measured at the distance r sub 1, 2 from the point charge is equal to 1 over 4 pi times epsilon naught, times the ratio of the charge Q2 to the distance r sub 1, 2. If we compare the two expressions, then we can see that the role of the 2 point charges are the same, and conclude that the potential energy U of a system of 2 point charges Q1 and Q2 is given by 1 over 4 pi epsilon naught, times the product of the charges Q1 and Q2 divided by the distance r sub 1, 2 between them. This result is equivalent with the expression, which we already obtained in the computation of the potential energy of a test charge brought to a given distance from a point charge. The potential U can also be written in the symmetric form, stating that it is equal to 1 over 2 times the sum of the charge Q1 times the potential phi2 at the point P1, and the charge Q2 times the potential phi1 at the point P2. Based on these findings, we can determine the electric potential energy or interaction energy stored in a system of arbitrary number of point charges. Let us consider the system of point charges Q1, Q2, ellipsis, Qn at the distances Ri from a given reference point O with the index I running from 1 to n. The potential energy U stored in the system is equal to the sum of the potential energy for each pair of point charges in the system, that is 1 over 2 times the sum of the potential energy U sub ij as a function of the distance r sub ij between the point charges Qi and Qj. In the summation, both the indices I and j run from 1 to n, and I is not equal to j. As an illustration, we show the distances between the point charge Q1 and the rest of the point charges in the system. We already saw that the potential energy U sub ij of the point charges Qi and Qj is given by 1 over 4 pi times epsilon naught, times the product of the charges Qi and Qj divided by the distance r sub ij between them. Then the electric potential or interaction energy U stored in the system is equal to 1 over 2 times the sum of 1 over 4 pi times epsilon naught, times the ratio of Qi times Qj to r sub ij from I and j equal 1 to n, while I is not equal to j. We can split the sum by writing the right-hand side as 1 over 2 times the sum of Qi from I equals 1 to n, times the sum of 1 over 4 pi times epsilon naught, times the ratio of Qj to r sub ij from j equals 1 to n, where j is not equal to I. Here we can recognize the electric potential phi I due to the all-point charges Qj but the point charge Qi at the point Ri, which is given by the sum of 1 over 4 pi times epsilon naught, times the ratio of Qj to r sub ij from j equals 1 through j equals n, where j is not equal to I. Then the potential energy can also be written as the function of the interaction potentials in the system, that is U is equal to 1 over 2 times the sum of the charge Qi times the electric potential phi I from I equals 1 to n. We can generalize this result for the electrostatic potential energy stored in a spatial volume with a continuous distribution of electric charge. Let us consider a given amount of electric charge distributed over a volume calligraphic V, which we can describe by the electric charge density ρ as a function of position. We could compute the potential energy stored in a system of point charge as the sum of the product of different point charges Qi and Qj in the system divided by the distance or sub ij between the charges. By applying the factor 1/2, we took into account the fact that each pair of point charges appears 2 times in the sum. In order to generalize this formula to the case of the continuous distribution of charge, we only need to perform an integration of the electric charge density over the given volume instead of the summation of the individual point charges. If the spatial distribution of the electric charge in the volume calligraphic V is given by the electric charge density ρ, then the electric potential energy U stored in this volume is equal to 1/2 times the double volume integral of the product of the electric charge density ρ evaluated at the positions R1 and R2 over the length of R1 minus R2, whereas the integration is performed over the volume calligraphic V. Here the position vectors R1 and R2 point from a given reference point O to the volume elements dV1 and dV2 of the double integral, and the distance between the volume elements is written as R sub 1 2. The factor 1/2 has the same role as in the case of the system of point charges since each pair of charge element is counted twice in the double integral. In this formula, we can recognize the electric potential phi due to the charge distribution ρ over the volume calligraphic V at the point given by the position vector R1, which is equal to 1/4 pi epsilon naught, times the volume integral of the ratio of the charge density ρ at the point R2 to the distance R sub 1 2, over the volume calligraphic V. Here the integration variable is determined by the position vector R2, and the potential is indeed a unique function of the position vector R1. We can substitute this expression into the formula obtained for the potential energy U, and drop the index from the position vector R, which is the integration variable now. As a result, we express the electric potential energy stored in the volume with a continuous distribution of electric charge as a function of the potential. That is, the potential energy U is given by 1/2 times the volume integral of the product of the electric charge density ρ and the electric potential phi over the volume calligraphic V. This formula is also general in the sense that we talk about the potential energy stored in a spatial distribution of electric charge. However, we can also consider an electric charge distribution over a surface calligraphic S described by the electric surface density sigma, and write the potential energy U stored in such a system as 1/2 times the surface integral of the product of the electric surface charge density sigma and the electric potential phi over the surface calligraphic S. Similarly, the electric potential energy stored in a continuous distribution of electric charge along a curve calligraphic C is equal to 1/2 times the line integral of the linear electric charge density lambda times the electric potential phi with respect to the arc length measured along the curve calligraphic C.